Today we're going to finish out chapter 18. This is all about something called neutralization, which is basically the reaction that happens when you add an acid and a base together. And really what we have when you add an acid and a base together, you're going to get salt water. Okay? It gives an example here. So we've got our magnesium hydroxide. And we can see that this is going to be a base. You can recognize the OH groups that are going to break apart. Okay. And we're adding that to hydrochloric acid. Okay. You have that hydrogen that will come off. And what we get, so the magnesium and the chlorine are going to, well, that's a salt. Okay, magnesium chloride is a salt. Okay. And so if we've gotten rid of this, we've gotten rid of that, what we have left, hydrogen, hydroxide, well, put those together, and get that. So when we neutralize acids and bases, really what we're doing is we're creating salt water. And of course, remember, in chemistry, salt doesn't just mean the salt that you would cook with. You would not cook with magnesium chloride because you really don't want a ton of magnesium. You do have some magnesium in your body, but you get too much of it, that's going to be a bad thing. So, but according to the chemistry definition of salt, we have salt water. Now we can actually use this to our advantage. So like I said, we're actually going to have a lab coming up here, and that is what we're going to do. We're going to be neutralizing acids and bases together. Now, what we are actually going to be doing is something called a titration. Okay. A titration allows us to figure out the concentration of either an acid or a base if we know the concentration of the other one. Okay. And we're going to go through exactly how that works. We're going to show you the tools and how we do titrations. But basically, what happens is you take whatever you're trying to determine the concentration of, and you add, what we're going to be doing is we're going to have an unknown concentration of acid. We're going to add a base until it gets to what we call the equivalence point. And that means, well, equivalence, that word should make you think of equal, okay? We add the base until we have the same number of moles of acid and base. And then based off of how much base we added, we can calculate the concentration of the acid. Okay. So we're going to be doing it a very low-tech way. When I was in college, we had computer-controlled equipment. that took a whole bunch of data, and then we went back and used a computer program to analyze the data. So it can be very, very advanced. Obviously, we don't have that kind of budget here, so we're going to be doing it a little bit lower tech. But anyway, in order to do that, we need to know a couple things. And so we're going to talk more in depth about titrations in just a minute. First, we want to introduce indicators. We've got some stuff here on there. All right. So you remember we talked about throw on some goggles because I don't want my eyes to get chemicals in them. Now these are not splash resistant goggles. So I'm setting a little bit of a bad example. When you go into the lab, you'll need to wear the splash resistant ones. But if I hurt myself, that's different than a student getting hurt. So now when we first talked about acids and bases, we talked about something called litmus. And I said that I would give an example of that. So this is litmus. Remember, there's red litmus and blue litmus. Red, if we see the color red, we're dealing with an acid. If we see the color blue, we're dealing with a base. Now that was just water. So it shouldn't be extremely acidic or basic. Okay. So if I get that in there, it doesn't really do anything. I'll take one of my blue litmus papers. Doesn't really do anything. But here I have some hydrochloric acid. Now remember, if we see red, it means we're dealing with an acid. Okay. Now that didn't really do too much to this red sheet, but if you pull a blue one out, you should start to see something. Okay. So you notice the blue turned red. That means we're dealing with an acid. It doesn't tell us much about anything like a concentration, but we do know that we're dealing with an acid. This is sodium hydroxide. We start with blue this time. Sodium hydroxide is a base, so we shouldn't really see much going on. Actually, even all the way in. So yeah. But again, we pull the opposite color. So once again, it doesn't really tell us much about concentration or pH or anything. It just kind of tells us, are we dealing with an acid or a base? We want to be a little bit more accurate. We can use something called pH paper. Now this will give us, you can see there's a range of colors that we can get that correspond to the different pHs. Pull one of these out. Do the same thing. Okay, we get that blue. You can compare it here. The pH of this is probably about 12. Okay, so it's pretty basic. We go to our hydrochloric acid. Okay. This is down here closer to between 1 and 2. So that gives us more information about what we're dealing with. Than just, is it an acid or a base? It's going to tell us how acidic. Okay. We can also test it in just plain water. Doesn't really change it much. We can compare this. Looks like this water is actually just slightly basic, maybe. But it's pretty darn close to neutral. So those are all useful. All of these are what we call indicators because they indicate what we are dealing with. Okay. This is something called universal indicator. If we aren't going to be using these strips, what we can do is use an indicator like this. Now notice, we put that in, a little swirl. So it's sort of a green color. You can see that. Maybe I'll put in a few more drops, make it a little darker. There we go, it's darker. So this universal indicator follows pretty much the same pattern that we find here. Very similar. The numbers don't match up exactly, but it's a pretty similar pattern. And so what we can do, if we take some of our sodium hydroxide here, put a little bit in, notice that we get this very deep color. Okay, and that tells us, looking at this, we can say, oh, okay, well, the blues and purples, they're basic. Then, of course, we can go the other direction. As that slowly neutralizes out, you can see that we're changing from basic to acidic. Okay. So that's a universal indicator. It gives us a wide range. Okay. You can actually see that there's still a layer of purple on the bottom because it hasn't mixed well. As it sits, that will all go to equilibrium. Now, for our titration, what we're actually going to be using is an indicator called phenolphthalein. Add water here. This is our phenolphthalein indicator. You'll notice it's clear. So if we put a few drops in, okay, it still looks clear. And the way that it works, you can see it actually has a little bit of color in there, because like we said, the water appeared to be just a little bit basic, which happens. But if we add some sodium hydroxide and really make it basic, it turns pink. Okay. But if we put it into the presence of an acid, sodium hydroxide is stronger than the hydrochloric acid that I've got, so that took a little bit to get rid of it. But in the presence of an acid, it goes back to clear. So, and you can go back and forth. Okay, we went from slightly basic to very basic, and then we can go back to basic with adding this. That may stay purple and may not, depending on how it goes as it comes to equilibrium. But this is what we're going to use, because with our titration, we're going to be doing hydrochloric acid and sodium hydroxide. And the equivalence point for that is really close to where this changes from clear to pink. It's close enough for us. Obviously, if we need super accurate results, we're going to use sensors that collect a bunch of data so that we can mathematically calculate it. But for this class, that's going to be close enough for what we need. Okay. If you notice on page 662 in the book, there's a list of a whole bunch of different indicators and where they change colors and what colors they go between. So obviously, depending on what you are titrating, you sort of have to know where approximately your equivalence point is going to fall on the pH scale so that you can pick the right indicator. Basically, what we are going to be doing in the lab, okay, is a titration. And we're going to use this. We're going to start with our acid and add base to it. Okay. Now, the tool that we're going to be using is this right here. So this is called a burette. Okay. And the way that it works, I actually took this off because I need to put a new one on. This one was starting to leak. So I'm not going to fill it up. But basically, you can see, this is going to connect. And then we have this, it's called a stopcock right here. Okay. If this lines up like that, things can flow. We twist it, and it's going to stop. Okay. On the burette, notice it has all these gradations on it. Okay. This one is actually filthy. I need to clean it. Looks like the last group that used it did not do very good. Anyway, I'll get that clean. Notice they start at 0 and go to 50. Okay. So what we're going to do, we are going to have a known volume of our hydrochloric acid. Now, you're not going to know what the concentration is. I'll know what it is, but you won't. You're going to have to figure out what it is. And so we put sodium hydroxide, and we fill it up. Now, we don't have to start right at 0. Okay. Sometimes I've seen people waste a lot of time trying to get it right at 0. Not important. All you need to know is where you started. because you just need to know how much was added. So if you started at 2.3 and you finished at 24.2, well, you just subtract 2.3 from 24.2, and that tells you exactly the volume that you added. Okay? So that's what these are for. They can tell you exactly how much of something you added. So we write down where we started, and we write down where the level of our sodium hydroxide is at the end point, and then that we can use to calculate the data. Okay? So it's going to look like this. Once again, this one is leaking, so I'll replace it before we actually have to use it. But this controls the flow. Okay? When it's like that, we have fluid coming out. When it's like that, we don't. Okay? Towards the end of, when you're getting close, you'll notice that sometimes it looks pink, but then all that pink goes away. That means you're getting really close to the end point. And at that point, you really want to try and go as slow as possible to get accurate results. It takes a little bit of practice, but you can actually get this where you can add 1 drop at a time. 1 drop at a time is the best practice at the end, because it's, is going to give you the most accurate volume. Because you can just keep adding and adding and adding, and it's going to stay pink. Really, you want to know right where it's going to go pink and stay pink, and nothing else, because that's your endpoint. You don't want to go past your endpoint. Okay? Now, once we have that data, then it is going to be then it's going to be a matter of doing some calculations. Now, in the lab, we're going to do this a couple times. I want you to do it at least 3 times, because one result isn't really good scientific practice. You want to do it multiple times so that you have confidence in your results. And then we're going to do the calculations to see what the calculation, or what the concentration is. Now, it's a pretty straightforward calculation. The book here on 663 gives the problem solving strategy, which basically is, now this is using sodium hydroxide, but it's also using sulfuric acid instead of hydrochloric acid, which is okay. I mean, it's the same strategy, just a very minor difference though. So calculate the moles of sodium hydroxide, okay? And what that means is, okay, so if we added, let's say we added 15.5 moles or milliliters, okay? You'll know the concentration of the sodium hydroxide, okay? And so it's, X moles per liter. Okay? Now that's not liters, so we do need to convert that to liters. Now we can do it before or after, as long as you put it in there, it's going to give you the same result. So we know that there are 1,000 milliliters in 1 liter. Okay? So now all of those cancel out, just like with moles. So you know how many moles of sodium hydroxide was added. From that, we do our stoichiometric ratio. In the example here that they're doing sodium hydroxide and sulfuric acid, remember we're going to get a salt and water, so we can pull out our water here, okay, which leaves us with sodium sulfate. Okay. Now, we do need to remember our ionic rules. So now we need to balance it. Pretty straightforward though. So 2 sodiums right there. And then that, we've got 4 hydrogens. And the 2 right there. And then basically, so we've got SO4, SO4, which leaves us just 2 other oxygens, 2 oxygens. So now we have moles of our sodium hydroxide. We want to know about this. But we know that for every 1 mole of this, we're going to use 2 moles of that. So that means in order to get to the equivalence point, we need twice as many moles of the sodium hydroxide as sulfuric acid that we started with. Okay. So since we're interested in how many moles we started with, we take the number that we got from here, divide it by 2, and that's the number of moles there. And once we have the number of moles, we divide it by the volume that we started with. Okay? So if we started with 25 milliliters, we divide however many moles of that by the volume. Let's do an actual example because there's a lot of things we were talking about that may not have really made 100% sense until we actually look at it and see what we do and do the calculation. So here, assume, let's see, so we've got a volume of 18.28 milliliters of 0.100 molar sodium hydroxide was required to neutralize 25 milliliters of a solution of methanoic acid. What is the molarity of the methanoic acid solution? Okay. So remember, we need a balanced equation because we do have to do some stoichiometry. So we have methanoic acid. It tells us that methanoic acid is HCOO. And we are adding sodium hydroxide. Okay. Now, once again, we know we're going to have water, so we can take the OH from there, and we can take one of the H's from here. So we get water. And that leaves us that. Actually, for whatever reason, with this, they don't put the cation first. So they write it like that. Sometimes that bothers me because you're normally supposed to put the cation first. But most of the time you'll see that compound written like that. Anyway, so as it turns out, this is already balanced, which makes our life easier actually. Okay. So we have 18.28 milliliters Now we do need to convert that to liters. We can do that right away. Okay. Because it tells us that we have 0.100 molar sodium hydroxide, which means we have this. So liters cancel out. Now we're just left with moles. That is going to tell us how many moles of sodium hydroxide went from our burette into our solution in order to neutralize it. This is actually nice math because it's all ones except for this. So it's just really moving the decimal around a bunch. And so what we get is 1.828 times 10 to the minus third moles of hydroxide. Now we, at this point, are going to apply our stoichiometric ratio, which is 1 to 1. So that means we started with 1.828 times 10 to the minus third moles of our methanoic acid. That's how many moles we had in the beaker to begin with. And now all we need to do is say, okay, this is how many moles there were. And we started with, as it says, 25 milliliters. Now we do need to, so molarity is moles per liter. So we're going to convert 25 milliliters to liters, which is that. You can't do it in your head that fast, no problem, just do the actual math. So we take this number of moles divided by that volume, and what we get is 7.312 times 10 to the minus second molar. Okay. So that's what we're going to do. The calculation sheet that I will give you walks you through all of these steps. So we'll practice that. Now, just so you know, I am skipping over salt hydrolysis in the book. Basically, there are salts that can interact with water to produce acids and bases. I mean, really, it's just an extension of Bronsted-Lowry. There are salts that can pull hydrogens or donate hydrogens, and it's, yeah. So anyway, we're going to skip over that, and we're going to finish out with talking about buffers. Okay. So a buffer is something that you can add an acid or a base to, and the pH doesn't really change. These are very, very useful because some reactions only will happen at specific pH ranges, including a lot of stuff in your body. Our blood is actually a buffer. So if your blood is not in the proper pH range, bad things can happen to you. And so your blood actually does a really good job of keeping things where it should be. And basically, with a buffer, we have either a weak base with its conjugate acid, or a weak acid with its conjugate base. the book gives an example of, we've got a mixture of hydrofluoric acid, remember that's a weak acid, and we have sodium fluoride. Okay. So this is going to break apart like that. Okay. And this will also break apart like that. Okay. Now, when we mix them together, okay, when we mix them together, this is the main reaction that we're interested in. So if we add an acid, we're increasing the concentration of H+. But remember, this is going to stress the equilibrium. We can apply Le Chatelier's principle. And if we increase the concentration here, it's going to move back that way. And so a lot of these H pluses are going to react with all of these available fluoride ions. Okay? And remember, we've got a bunch more of these fluoride ions from the sodium fluoride that we added. Okay? And so they react with this. They turn into HF, which does not contribute to the pH. And so, even though we've added acid, a lot of that acid just reacts with the fluoride ions and forms that. And so the pH doesn't really change. If we add a base, well, remember the base is going to create a bunch of hydroxides. Well, those can react with the hydrogens here. But as these get used up, remember this is a weak acid, so we've got a whole bunch of this left. So it can move over, and once again, the pH stays pretty close to the same. Now, they do have limits, okay? If you use up all of your buffer, then the pH is going to change very rapidly as you continue to add. But as long as you still have whatever it is in your buffer system available, your pH is going to change very little. Okay. Different buffers will be at different pHs depending on what they are made out of. Okay. Depending on the strength of the acid. I mean, they're all weak acids, but the Ka value. Because if you have a higher Ka, you're going to have more H+, which is going to be more acidic naturally. If you have a lower Ka, well, you're going to have less here, so the pH is going to be a little bit higher, less acidic. You can also have buffers that, instead of using an acid, use a base. Same thing, except that buffer is going to work in the base range. So buffers basically are there to keep things in a specific pH range. So, now, before we finish up, so I do have the lab procedure. These are all of the instructions for the lab. We're going to actually do the lab next time. So we'll go down to the lab and we'll actually start using chemicals and equipment and stuff. Just remember, we will need to use proper safety precautions, all of the things that we talked about or that are on that safety sheet that I handed out. So for part of your homework, I just want you to read through this and make sure that you have a general idea of what's going to happen. Okay. This is going to be our data sheet. Okay. Everything right here, these two top, that's the data that we're going to collect during the lab. Everything below that is calculations. But it walks through all of these calculations that we did on the board. Okay. So you have your volume, you calculate how many milliliters, you change that to liters, calculate the number of moles, calculate the number of moles of acid, if that was the number of moles of base. The volume of acid, now this one is filled in because we're going to use 20 milliliters, and so we already know that. And then we can use that to calculate the concentration. And then the last one, it's the average. You don't need an average for everything, you just need one average of all your trials. So I will give this to you, like I said, just give it a quick read, make sure that you understand what's going on. Ask questions. And then, instead of homework out of the book, I've got this. This is just basically 5 different titration calculations. So just like what we did on the board, just like example problem 6 on page 664. Okay. It's going to give you how many milliliters of what you added, how many milliliters of what you started with, and the concentration of what you're adding. Okay. And then you just need to find the concentration of whatever the unknown is. So there's 5 different things. Like I said, this is going to be the same calculation that we do for the lab. Right? So I've got this. I'll also put it up on the LMS class wall in case we lose this or whatever. So it'll be there. But yeah, this will be practice for doing the calculations for the lab. And next time, we'll actually go into the lab and do some chemistry there. So I'll give this to you. You can start on this homework.